Hello and welcome to this lecture. In this lecture, we are going to carry on our study of limits and continuity. Especially, we are going to look at these functions, two specific functions. So far, we saw polynomial functions, rational functions, constant function, identity function, very simple functions. We are going to slightly complicate things by looking at powers and exponentials, x power a and a power x, right. So, this x power a and a power x for real values of a is a slightly more complicated function, and proving things and all is slightly more difficult, but they show up all the time in applications. So, you should see them, you should understand limits of them, understand continuity of them. So, in this case I am just going to give you the result, and maybe you can look up some proof on your own, or maybe in the forum you can post some proofs if you know the proofs. This is something you can look at. I am not going to prove many of the results here. I will just state the results and we will use it in solving problems. Okay. So, here is the main result. Okay. So let's start with sequences first. Okay. So, I am going to start with sequences before I jump into limits of functions. We know limits of functions and limits of sequences are very intimately connected. Okay. So, here is the problem I am looking at, right. I have a sequence an which converges, okay, and then I have a real number b. Okay. I am going to look at two other sequences. The first sequence is an power b. The other sequence is b power an. Okay. So, this is the exponentiation with b as the base. This is the power with an raised to the power b. Right. So, this is the power function. This is the exponentiation. Okay. You are powering an by b. You are putting b as the base and taking a to the exponent. You are exponentiating with a, right, with b as the base. Okay. So, let us say that the sequence a1 to a1, a2 so on converges to L. Then it turns out for a real number b, the sequence a1 power b, a2 power b converges to L power b. Okay, of course, this L power b has to be well defined. What do I mean by well defined? Suppose b is negative and L is 0, right. I do not want to be inverting, doing 1 by 0 or something here. Okay, so such things should not happen, or maybe L is 0 and b is 0. So, I do not want to do 0 power 0 and all that. So, as long as this L power b is well defined, this a1 power b, a2 power b, etc. will converge to L power b. Okay. So, the powering operation is sort of well behaved with taking limits. Okay. You have a sequence which is converting to a limit. You hit it with the powering function, like raise it to the power b. The limit also goes the same way. Okay. So, this is a slightly tricky thing to prove. We could prove it, but it will take us too far afield from the nature of this course. So, we are not going to write down a proof for this, but nevertheless, it is a very powerful thing, and this lets us do a lot of non-trivial things. As you will see in this example below, we can do limits for all these sort of expressions using these results. Okay. The next result is also equally powerful. It says something very similar is true for the exponentiation operation. You take this sequence and do exponentiation with the base b, b power a1, b power a2, so on. Okay. That sequence converges to b power L. And here again we will assume this b power L is well defined. Okay. The values of b and L are such that b power L excuse me, b power L is well defined. If b power L is well defined, then this sequence b power a1, b power a2, so on converges to b power L. Okay. So, this is a theorem. This of course needs proof, and we are skipping the proof here. It can be proved, and that gives us so much power, right? Power and exponentiation. It gives us both in one go. Okay. So, it's a fantastic result. How are we going to put it to use? Here are a bunch of examples. If you look at the first one, it's 1 by n power 1 by 10. Okay. So, this is not something that gets covered by our basic example and the properties we had for multiplication, division and all that, right. So, it's n power 1 by 10, n power 0.1. How do you do it? But then look at this result here. You have 1 by n raised to the power 1 by 10. 1 by n converges to 0. So, this is just 1 by n raised to the power 1 by 10. So, you use the first result and you take the limit 0 power 1 by 10, and that is just 0. See how easy it is to do limits like this when you have this power rule. So, you have the power rule, you can call this the power rule and the exponentiation rule. You use the power rule here, the fact that power and limits play very well with each other, you can do it. Okay. Same thing with this one, 2 power 1 by n. Okay. When you do 2 power 1 by n, how do you do limits for this? 1 by n, the limit for 1 by n is 0, we know that. Now 2 power n, you simply use the exponentiation rule, you are exponentiating with 2. So, the limit will simply be 2 power 0, which is 1. See how easy it is to do this. Okay. So, basically the limit will go inside the powering operation. Okay. So, 1 by n power 1 by 10, limit will go inside the 1 by 10. Likewise, here 2 power 1 by n, limit will go inside the exponentiation. Okay. So, this is the way to read it. So, let me just write that out for you. Okay. So, the way to read this is basically limit as n tending to infinity 1 by n raised to the power 1 by 10 is the same as limit as n tending to infinity 1 by n raised to the power 1 by 10. So, this is what I meant. So, now you have 0 power 1 by 10, you can do very easily. Same thing with the second one, limit as n tending to infinity 2 power 1 by n is the same as 2 power limit as n tending to infinity 1 by n, and that is 2 power 0, and that is 1. So, this operation, right, this is the operation which is facilitated by the power rule, and this is the operation which is facilitated by the exponent rule for limits. Okay. So, this adds to our arsenal for computing limits. Look at this guy now. Okay. Limit as n tending to infinity square root of 2n squared minus 5 by 3n plus 5. If you just put n equals infinity, I am going to get infinity by infinity here, right. I may not be able to deal with this so peacefully. So, what is our trick here? When you have this n in the numerator, n in the denominator, I am going to divide by n. Okay. So, in this case, I have to divide by n. Let me show you how this works. Square root of 2n squared minus 5 by, what exactly did I have? 3n plus 5. Okay. So, I am going to divide by n. So, I will get 1 by n square root of 2n squared minus 5 divided by 1 by n 3n plus 5, right. So, I have divided numerator and denominator by n. This n, when it goes inside the square root, becomes n squared. Okay. And this will simply remain as it is. So, I will get 3 by 5 plus n. So, once it becomes n squared, I am going to have 2 minus 5 by n squared by 3 plus 5 by n. Now, I am ready to take limits. So, when I take limits now, I know because of the power rule, I can take my limit inside the numerator and denominator, that I knew before, right. I did not need power rule for that. 2 minus 5 by n by 3 plus 5 by n. Now, this limit can go inside the square root, that is facilitated by the square power rule. So, limit as n tending to infinity 2 minus 5 by n. This I could not do before, I am sorry, limit as n tending to infinity. So, this is just 3 here. So, this I could not do before, this is by the power rule. Right. So, this limit went inside the square root, that happened because of the power rule, and now I go in, I am just going to get 2 here and then the square root 2 by 3. How nice is that, right. So, previously we could not do these kind of limits, and now because of the power rule we can do them. Okay. So, here also I am not going to do this in great detail for you. Square root of 3 plus 1 by n times 12 minus 1 by n, limit will go inside the square root, and then there is product, again limit will go there, 1 by n is 0, minus 1 by n is 0, square root of 3 into 12 is 36, that is 6. Okay. So, this limit works out to be 6. What about this guy here? 3 power root n divided by 3 power n. Okay. So, if you just literally do the limit here, it seems to go to infinity by infinity, and we have to figure out which one is the bigger infinity. Okay. So, then you can do this problem. So, let us see, let us do that figuring out here. Okay. So, I have here 3 power root n by 3 power n. Okay. So, you can do it either way, but I am going to do it as 1 by 3 power n minus root n. Is that okay? Hopefully, you saw this. So, it is 1 by 3 power n minus root n. You can also do it the other way. You can also push the n there and write it as 3 power root n minus this. So, this would go as 1 by 3 power n times 1 minus 1 by root n. Is that okay? Hopefully, that is okay. So I'm just arming myself to take a limit suitably. Now I'm ready to take limits. So if I take limits as n tending to infinity, 3 power root n by 3 power n, it's the same as 1 by 3 power, limit can go all the way there, limit as n tending to infinity, n times 1 minus 1 by root n, and that's, oops, oh, let me write it differently, sorry. So this one I can write as 1 by 3 power n into 1 minus 1 by root n. Okay, so this is a better way to write it. So I have here 1 by 3, limit as n tending to infinity, 1 by 3 raised to the power n times 1 minus 1 by root n. My limit can go in, and when it hits this guy, this tends to 1. Okay, so I simply get here limit as n tending to infinity, 1 by 3 power n, and that I know is 0, right. So 1 by 3 power n, it's r power n, where r is less than 1. There is one such limit we know, and anyway the limit you know here is 0. So this guy is going to go to 0 limit. Okay, so 3 power root n is smaller than 3 power n, and asymptotically 3 power n dominates, so you get 0. Okay, so and the proper way to see it is here. A lot of people get a little confused by this. They say limit went in, so you took limit here, why is this n still there? I didn't take limit there for n, right? So this limit still holds. So this is what these limiting rules allow me to do. If I have part of a function somewhere where I can apply limit, I should just go ahead and apply that limit there. And as long as that limit is finite, I can do it. There's no problem. It won't come back to bite me. Okay, wherever you can, partly you can apply the limit, not fully. Keep the limit there, and then if you see, notice some part of it, oh, that's going finite, apply the limit there. It's okay. That kind of operation you can do. Of course, it will take a little bit of care, but that will work. So that's what I've done here. Notice these kind of tricks, these are very important. I had this complicated type of function here, but there was a part here which was going to a constant, right, finite when n goes to infinity. So you can apply the limit there and get rid of it, and then work with the rest, and still the limit will be there, but the remaining part will be easier to be handled. Okay, so this is something you can do. This comes because of the limiting, the combination of limiting rules and all that. Okay, I hope you see that. I hope you saw how my limit can go out into the exponent and all that. This was facilitated by the exponent rule, right? So this was because of the exponent rule. Okay, so we could do it. So you can do problems of this variety. Here's a problem which is sort of like this. You have to figure out, see, this is n power half, the n power 1 by 3, n power 2 by 3. So this 2 power n power 2 by 3 is sort of going to dominate, right? He seems like the big brother. So you have to divide by this 2 power n power 2 by 3, and then take it up there, and then do each of these things separately, and then argue it out. My hunch is this limit is going to go to 0. Okay, I'll urge you to do a similar argument, and you will get 0. So each of these things you can do separately and then add it up also. Okay, so you will get 0. I'm very confident you will get 0. Okay, so work this out. I'll leave this as an exercise for you. Okay, so you see the sort of problems we're able to do with this power rule and exponent rule. It's really, really powerful. Okay, all right. So we have seen sequences where this exponentiation and power were acted upon, and we could predict their limit. Anytime you can do something for sequences, you can do something for functions as well. Okay, so that's the functions we're going to. We want to go to limits of functions x power a and a power x. Okay, so let me first take x power a. Supposing you have a sequence a1, a2, so on, that converges to x0. What's going to happen to a1 power a, a2 power a, so on, by my power rule? It's going to converge to x0 power a. Okay, so guess what I have here? Limit as x tending to x0, x power a is actually equal to x0 power a. Okay, by the limit. So when you want to do limits of functions, it's better to do limits of sequences first, right? So limits of sequences give you directly what the limit of function should be. Okay, same thing with a power x. You have supposing you have a sequence a1, a2, so on, converging to x0. Okay, a power a1, a power a2, so on, converges to a power x0. So this clearly means for the function a power x, limit as x tending to x0 of a power x is a power x0. Okay, so you see here the other wonderful result by which we can say both these functions x power a and a power x have limits at all points where they are well defined. They have to be well defined. So it turns out this x power a and a power x can be a bit dicey. Like for instance, if x goes negative and a is a fraction or something, then it's not defined. So all those are still there. Wherever it is defined, and well defined, these functions are going to be having limits at all those points, and clearly by the same argument, they will be continuous wherever they are finite and well defined as well. Okay, so these functions x bar a and a bar x are really well defined because of the power rule and the exponent rule of the limits. Okay, so that's very nice to see. Let's put it to use for finding limits of functions. Once again, these problems are from Thomas's calculus textbook, and you can also comment on continuity here. Okay, let's quickly go through these problems. These are very similar in flavor to the problems you saw with limits computation, except that I put lots of square roots and powers and all that. Some people get scared by looking at these kind of functions. I want some of that fear to go away. That's why I've put a lot of functions here. Let's begin with the easy ones. The top two are very easy. This is just simple substitution, right? Limit as x tending to 4 square root of x squared minus 10. Okay. Now, what do I know about square root? This is a power thing. So, limit can go inside the power. Okay. So, previously limit was going inside polynomials, going inside rationals. Now, limit can go inside power for functions also. That's because I know x power a is continuous, right? So, limit will go in. So, you will just substitute x equals 4 here. So, square root of 16 minus 10 root 6. Easy enough, right? So, here again you have a problem where you have h tending to 1, square root of 6h plus 10 minus 5 divided by h. You can simply substitute h equals 1 here. So, you will get 6 plus 10, 16, 4, 4 minus 5 minus 1 by 1 minus 1. So, this limit just ends up being minus 1. The fact that the substitution is okay is because you have square root, which I know is continuous operation, right, continuous function. So, you can put the limit inside, whether the limit is outside or inside, it's the same thing. So, you get the answer. Okay. I hope you see how that result is used. The fact that the limit of x power a, the x power a is a continuous function. So, the limiting value is equal to the value taken by the function there, right. So, you can just substitute, the limit will go in. That's what it means when I say when you can substitute. The limit goes inside the power, right. Limit as x power a as x tending to x naught. Okay, let me just write that down. See, limit as x tending to x naught x power a is x naught power a, which what is this x naught? Is limit as limit of x. So, maybe I should write that down here for you to drive home the point. Okay. So, limit as x tending to x naught x power a is the same as limit as x tending to x naught x raised to the power a. Okay. Is that okay? So, this is the big deal, right. So, anything you have here, you can put the limit inside, then this will work. Okay. So, this x could be anything else, right. Okay, anything else you have there also, it will work. The same thing with u power x, right. Limit as x tending to x naught a power x is a power limit as x tending to x naught of x. Okay. So, the limit goes through inside, right. The limit sort of goes inside the power, then becomes raised. Likewise, here the limit goes inside the exponent. Okay. So, this is the rule that we use here when we do these limits. Okay. I have square root, but my limit can go inside, and this is just a substitution. Likewise, here limit numerator denominator, it can go inside, then you end up with a substitution. Okay. I hope you sort of get a feel for what that is. Okay, all these other problems, let's maybe do some of the easier ones. This one again is a simple thing of square root and x, this and all that. There's no 0 by 0 here. It's just a substitution of x equals 8 here. Square root of 16 is 4. If you put 8 here, 8 power 1 by 3 is 2. You get 2 power 4 minus 3, 2. So, I guess this will be just 8 or something, right. So, this is an easy substitution. What about this one here? This one is also an easy substitution because you've got only exponent, square root and ratio. The limit will go to the numerator, limit will go to the denominator. It will be just 2 plus 5, 7 divided by 4 plus 2 plus 1, 7. This will just be 1. Okay. There's no problem with these two also. Okay. These 4 guys, I will do maybe the first one here. Okay. What happens here with this one? X tending to 1, you get 0 here, you also get 0 here. Okay. Now, these kind of problems, when you have a rational expression, when you have a numerator denominator and there is a square root, a very common trick you can use is to get rid of the square root in the denominator or in the numerator. Wherever you have a problem with the square root, you can get rid of the square root, whether it's in numerator or denominator. Let me show you that little bit of a trick. It's very easy and elegant. I'm just trying to remember the exact formula here. It's x minus 1 divided by square root of x plus 3 minus 2, isn't it? The trick is to multiply and divide by square root of x minus 3 by 2. This is an invaluable trick to get rid of square roots. Okay, wherever you have square root, this will be gone. So when you have this, you have a plus b, a minus b into a plus b, right? You see that? A minus b into a plus b. So this will end up being a squared minus b squared. Okay, so that the numerator you can keep as it is. There's no problem. Square root of x plus 3 plus 2 became plus 2, right? Plus 2 is not problematic for you. Minus 2 is a problem. So you get here x plus 3 minus 4. And what is x plus 3 minus 4? That's the same as x minus 1, and it will cancel. Okay, so this ends up just being square root of x plus 3 plus 2. Okay, so this is a invaluable trick, okay, that gives you a lot of wonderful ability to manipulate and ability to ask a lot of questions in exams and all that. So it's very useful. So this ratio is the same as this ratio. Okay, so once you have it, limit is easy. So limit as x tending to 1, square root of x plus 3 plus 2. So you take your limit inside. So you just get 2 plus 2, which is 4. Okay, so x is 1, square root of 4 is 2, plus 2, 4. The answer is 4, right? So notice how I did this little trick here by using this multiplying numerator and denominator by something and then changing and getting rid of something. Okay, so this problem you can do the same trick, except you have to do it in the numerator, right? So you can anyway multiply and divide by square root of x squared plus 8 plus 3. Okay, and then you will see wonderfully well this x plus 1 will cancel. And then whatever you are left with, you can substitute x equals minus 1 and you'll get the answer. Okay, so that's the way you do this problem. What about these guys? They look very notorious, but they're actually very similar. Let me do this one and show you. I mean, these are all tricks, the same tricks. Some factoring has to happen, right? See what happens here. If you put x equals 9, I get root 9 is 3. So that's just 3 minus 3 is 0. Likewise here, if I put here also, I will get 0. So I get 0 by 0. So somehow this form has to cancel, and this is not a polynomial now, right? So this is not a polynomial. When it's not a polynomial, it seems to be a bit dicey. You can do many things here, but then again, I mean, you to slightly sort of notice what's going on. Okay, so you have here 9 power root x by 3 minus 9 divided by 3 power root x by 3 minus 3. So the trick is to notice 9 is 3 squared. So it is 3 root x by 3 whole squared minus 3 squared divided by 3 root x by 3 minus 3. It's just that's all. Okay, and then this is a squared minus b squared. So you get 3 root x minus 3 minus 3 times 3 root x by 3 plus 3. Okay, so this is just bread and butter simplification. Okay, and then this will cancel and you get 3 root x by 3 plus 1, and then limit as x tending to 9 of 3 root x by 3 plus 3 is just 3 plus 3, and that's 6. Okay, it's done very cleanly. Now, this kind of trick of cancelling numerator denominator, you might say, why should I do all this? This is mathematics. I want to be electronics engineer, etc. But this kind of trick in a different form shows up in some designs of things also. This being able to deal with numerator denominator rational forms of different types is, believe me, quite important. Maybe not in the same root x by 3 form, but there are other cases where you'll see knowing numerator denominator, what happens when denominator goes to 0. All of these things will come back and haunt you later on when you do electronics as well. So this one is very simple. It's again a same a squared minus b squared type formula. Identify the numerator denominator, and you'll get to the answer. Okay, I'm not doing this in great detail. I think you'll be able to figure this out. Okay, so I hope this notion of powering and exponentiation, the power rule and exponent rule, you're able to get to. That's very, very important. It's very, very useful, and as you take exponents and square roots, limit is going to be well behaved. Continuity is going to be there. Okay, the continuity is also important, right? All these functions are continuous wherever they are well defined. Okay, so that's nice to see, and that's very useful as you look at these kind of functions. Okay, so that's the end of this lecture. Hope this was interesting to you. We'll meet again in the next lecture. Thank you.